All right, welcome for section 8.2. I'm just gonna enlarge this a little bit and then fix my pen. Sorry, I should have done that before I started this, but welcome to section 8.2. In section 8.2, what we're gonna talk about is arithmetic sequences. That word is pronounced arithmetic. If there was an A here, that's arithmetic, but we're looking at arithmetic, the adjective form of that, sequences, and partial sums. So without realizing it, you guys have actually done arithmetic sequences in section 8.1. And when you're doing that homework, there's some sequences that are arithmetic, there's some sequences that are geometric, and then there's some sequences that are neither of those. So here, we're going to look at just arithmetic, and then in section 8.3, we'll look at just geometric. So first, by definition, an arithmetic sequence. A sequence is considered arithmetic if the difference between each set of consecutive terms, so the difference between each set of consecutive terms, is constant. So the sequence a sub 1, we're just writing out an example sequence, comma, a sub 2, oh, wow, that's not showing up as a's at all. For some reason, in all these videos, a's become a problem. A sub 2, comma, a sub 3, so on and so forth up until a sub n, and then continuing after that. So we have some infinite sequence. In that sequence, it is considered arithmetic if a2 minus a1, the difference between these two terms, is equal to a sub 3 minus a sub 2, the difference between these two terms, is equal to a sub n, a sub n minus a sub n minus 1, the difference between this term and the term that would come before it, is equal to d. That number d is what would be the common difference, is what it's called. And that common difference, what that really is just saying, what number is being added or subtracted over and over and over again. So, summary of this slide, I guess. An arithmetic sequence, that is a sequence where you are adding the same number over and over and over again. And by adding, that could mean adding a positive or negative integer. So you could sort of think of it as adding or subtracting the same thing over and over. All right, so side 2, we have determined if the following sequence is arithmetic. So just determine, is this arithmetic? When we do that, we start at this first term and we say, okay, the difference between these is 3. The difference between these is 3, and the difference between these is 3. So again, I added 3, I added 3, I added 3, so yes. And further, we can say that d, the common difference, the thing that's being added, is equal to 3. This will be helpful when we write some formulas. Next, from 10 to 6, what I'm doing here is subtracting 4. From 6 to 2, I'm subtracting 4. From 2 to negative 2, I'm subtracting 4. So I'm adding still the same thing, which makes this yes. The thing that I'm adding is a negative 4. Again, you could sort of think of it as what I'm subtracting is 4. All right, so we have 2 arithmetic sequences there. I know I am doing an example problem in the notes, by the way. This is the only, I think, set or slide of examples that I'll do. Then you could watch the other video that will have all the different examples in it. So now we have 1, negative 2, 4, negative 8. We're only concerned right now with addition and subtraction. That's, arithmetic. So from 1 to negative 2, I subtracted 3. From negative 2 to 4, I jumped ahead, I added 6. I don't care what happens after this. No. It is not arithmetic because right away I'm doing something different. Now you could have looked at this and said like, oh, I'm multiplying by negative 2 each time. Okay, cool. You're a little bit ahead. That's geometric. That's in a couple days. For right now, no, it's not arithmetic. I'm not adding or subtracting the same thing. Here, I added 1. Here, I added 2. So no. Not a very good n. No. There we go. You don't have to state what d is. There is no common difference because it's not arithmetic. All right, moving along. Next slide. Writing a formula for an arithmetic sequence. So some of you may have been struggling in section 8.1 on the questions that said to write the formula for the sequence. The good news is a lot of those are arithmetic sequences, and there's a formula for that, so it gives it a little bit more structure. And then the better news is the geometric ones that you have, also have a formula, so that'll make those ones easier. And then the other ones that will really have to require a lot more thinking will be the ones that are neither arithmetic or geometric. All right, so the nth term of an arithmetic sequence has the form of a sub n is equal to n times d plus a sub 0. Now, there's a couple different types of formulas. This is what's considered an explicit formula. And the reason it's considered an explicit formula is because it relates the term number to the term value. So this is directly relating, hey, I'm looking for the 5th term, and I have a formula for the 5th term. Explicit formulas allow you to jump further along or infinitely along in a sequence. The other type of formula is what's called a recursive formula. And a recursive formula is a little bit different. We'll talk about that still. But just know, okay, this is explicit formula, where D represents the common difference. Again, that's the thing that's being added or subtracted. And A sub 0 is the term previous to the first. So a sort of issue comes up with this in that you do have to think about like what would be the term before the first term. There's technically a formula for this. I don't see many people, write the formula too often. You're more than welcome to. Obviously, don't let that discourage you. But we're essentially saying that the previous term, a sub 0, is the first term minus the common difference. And I lied to you a slide ago. We are going to do another slide of examples just because they're quick examples and it gives you at least something to relate to. So we're going to do this next slide as well. Find the formula for the nth term of the given sequence. So quick, easy things. When I look at this, first thing I want to do is figure out, are these even arithmetic? So what I'm going to do is look at the difference here. 5, 5. So D is 5. The other thing I need is a sub 0. A sub 0 means what was the term that would have come before 3. So if you realize I added 5 each time, so going in the left direction, or going in the past, I would be subtracting 5, and this would be negative 2. Our formula for this is n times d plus a sub 0. N is a variable. Sorry, this says a sub 0. Let's erase that. I know. You can yell at me, scream at me all you want. I'm just going to move it over here, but it's going to say a sub n. So I'm looking for a sub n. Oh, now I remember why I had a sub 0 though. Okay, so we have a sub n here is equal to n times d. Well, d is 5. N is a variable. So we're just going to put in n because we want to write a formula for the nth term, plus the previous term, the 0th term, if you will, which is negative 2. So minus 2. That's it. You didn't have to look at this and be like, okay, n is 1. I'm multiplying by 5 and then subtracting 2. N is 2. I'm multiplying by 5 and subtracting 2. The explicit formula, n times d plus a sub 0, allows you to do that without necessarily thinking through what is the pattern. All right, here. we have, let's change the color. I know we use red all the time. Subtract 3, subtract 3. So again, we have to think of what was this term that would have come before this. So I'm subtracting 3 each time, which means in the opposite direction I'd be adding. So this would be 28 for a sub 0. D is negative 3. So don't need that line. We have a sub n is equal to d, negative 3, times n, plus a sub 0, 28. Super easy. Look at that. It's a breeze. Man, it's going to be a fun chapter. All right, so switched our color again. Here I notice I'm adding 15. I'm adding 15. So D is 15. In the past, A sub 0. I added 15 each of these times. So going in the opposite direction, I'd be subtracting 15, which puts me at negative 5. So we'll have A sub n, terrible A as always, is equal to 15n minus 5. If you have questions on those, just jot down the question at the left or right of the slide and make sure that you ask it tomorrow at the beginning of class, or whatever day. I don't know when you're listening to this. It could be in the past, the future. Who knows? Nobody's here. Okay, using recursive notation. So we just got 2 more slides. Bear with us, or me. Using recursive notation. So if we have the sequence a sub 1, that's not a 1. A sub 2, a sub 3, and so on and so forth until a sub k. We do switch it for recursive. So instead of n, it's going to be k. And then we go a little bit further and just say a sub k plus 1. This a sub k plus 1, what this really means is just the next term. So regardless of what k is, a sub k plus 1 just means the term that comes after that. So some sequences are recursive, meaning that they are defined not by the term number, but by the previous term. So for instance, if I have a sub k plus 1 is equal to a sub k plus 2, such that a sub 1 is equal to 5, what this is really saying is, okay, I have a first term in my sequence, that's 5, and the next term is equal to the current term plus 2. That's a really fancy way of, it's a really fancy way of saying and writing what all of you sort of see in your patterns. This is just saying I'm starting at 5 and adding 2 each time. So our sequence is starting at 5 and adding 2 each time. We don't know where we're stopping. It doesn't tell us to. So, looking back here, just to jump back a slide, if I was looking at this, what I wrote here is the explicit formula. What it related was the term value, like 18, for instance. I had no relationship to 3. I related it to its term number, which was 2. A recursive formula is where you say, I'm not going to relate that 8 to term 2. I'm going to relate it to the term before it. So we're no longer concerned with the current position in the sequence. We're concerned with the pattern a little bit more. If you look at a pattern and you're like, oh, I'm subtracting 7 each time, well, it's very easy to write a recursive formula because that's what you're essentially going to say is I'm just subtracting 7 from the current term. Sort of nonsensical. But for some reason, recursive notation is what throws people off a little bit more than explicit notation, even though it's the one that you're used to thinking about in the first place. All right, we're going to skip the next example and go on to this last slide for us. So just skip a slide, then you have sums of finite arithmetic sequences. So we're talking about a sum of a finite sequence, which means that it's ending, it's not infinite. And we have a formula for that. I don't know, I've got space up here, but I'm not going to put anything there. So the sum of a finite arithmetic sequence can be found by using the formula S sub n is equal to n divided by 2 times a sub 1 plus a sub n, where this S sub n just represents the sum, n represents the number of terms that we're taking the sum of, a sub 1 represents the first term, and a sub n represents the last term. So just a quick formula for the sum of a finite arithmetic sequence. If you're thinking about, well, wait, Mr. Davis, what about the sum of an infinite arithmetic sequence? Well, then you sort of need to think that through a little bit, because an infinite arithmetic sequence means that I'm adding some number over and over and over and over and over again. So there's not going to be a sum, because it's just going to keep going on infinitely. That's sort of unique to something that's arithmetic, by the way, because when we look at geometric, we see that we can take the sum of certain geometric infinite sequences as well as finite sequences. You can always take some of those, I think, for the most part. All right, yeah, so that's going to be the end of our notes. Feel free, there is going to be, an optional video. By optional, I mean it's just going to cover all the examples. So feel free to watch that and feel extra prepared for class.